If you are an elite center forward in a water polo match and you get pushed backward just 3 feet by a defender, your chances of scoring actually plummet by nearly 30%.
Oh, yeah. It is a massive drop.
Right. I mean, 3 feet. A single yard of lost territory essentially kills the entire offensive play. But here is the really crazy part.
Okay. What is it?
Until now, coaches and sports scientists, they had no scientifically reliable, sport-specific way to measure the sheer physical strength it takes to hold that ground.
It really is a phenomenal blind spot in sports science. We can measure the ground reaction force of a sprinter down to the absolute millisecond.
Yeah, exactly.
And we can quantify the exact wattage a cyclist generates on a tough climb.
Mm-hmm.
But measuring raw tactical strength when an athlete is, well, submerged, constantly moving, and essentially fighting in a fluid medium.
It's nearly impossible.
Right. It completely defies standard biomechanical testing.
And that unseen underwater battleground is exactly what we're exploring today in this deep dive. We are looking at a brilliant piece of biomechanical engineering designed to solve this exact problem.
It's a fascinating study.
It really is. To be specific, we are unpacking a paper titled Analysis of Pushing Forces During the Water Polo Eggbeater, Reliability and Validity of a Novel Approach.
Yes, great paper.
It was authored by Félix Croteau, Elouan, Lanoé, and Julien Clément, and it was published in the Journal of Sports Science and Medicine on March 1st, 2024.
So our mission for this deep dive is to explore the profound biomechanical challenges of measuring sport-specific strength in aquatic environments.
Which, as we've established, is no small feat.
Exactly. We are going to analyze how this research team engineered a highly reliable, really accessible testing method to actually quantify the complex physics of water polo players holding their territory in the pool.
Right.
We need to understand why this was so notoriously difficult to measure in the first place and, the ingenuity of this solution they finally built.
Okay, let's unpack this. Because to really appreciate the scale of the problem these researchers tackled, you have to mentally step away from the surface-level view of water polo.
Well, for sure. Most people just don't see what's happening underneath.
Right, like if you just catch a game on television, you see players swimming, maybe passing the ball, definitely some splashing. It looks like a swimming competition with a ball.
That's the illusion.
But the true tactical reality is that water polo is a brutal, relentless game of territory. It is all about spatial dominance.
Yeah, the center forwards and the defenders, they're engaged in a constant wrestling match.
Constantly.
Their entire objective is to establish and maintain a physical anchor in the water directly in front of the goalkeeper's cage.
Which brings us back to that wild stat.
Yes, as you mentioned earlier, the paper explicitly notes that staggering 29% drop in scoring probability for every meter a player is pushed away from the center.
It's wild.
You weren't just trying to outswim someone, you were trying to become an immovable object in an environment that has literally no solid surfaces.
I try to visualize the physical demand of that, and the best comparison I can really think of is trying to win a sumo wrestling match while treading water in a bottomless pool.
Oh, that is a fantastic analogy.
Right, because a sumo wrestler on land, they use the floor. They plant their feet, they drop their center of gravity, they create friction, and they use the earth as leverage to push their opponent.
Exactly. They have a base.
But in a deep pool, you have zero solid ground. You cannot plant a foot.
And that analogy perfectly isolates the biomechanical hurdle here. To generate leverage without a floor, water polo players have to rely on a highly specialized, incredibly taxing movement called the Eggbeater kick.
And just to be clear, the Eggbeater is not your standard flutter kick or like the frog kick you learn in basic swimming lessons.
No, not at all.
It is a continuous alternating circular movement of the legs. So one leg sweeps clockwise, the other sweeps counterclockwise. You are essentially turning your legs into twin outboard motors.
That's exactly what it looks like mechanically.
Yeah, creating this constant downward and backward vortex of water. And that vortex has to produce both upward buoyancy to keep your torso above the water and simultaneous horizontal pushing force to actually fight off the defender.
The complexity of that neuromuscular firing pattern is just staggering, honestly. You are asking the human body to perform an asymmetrical, continuous rotary motion just to generate linear force.
Which sounds exhausting.
It is. And for the longest time, the measurement gap in the sport regarding this specific movement was massive. Coaches obviously wanted to know which of their players possessed the strongest Eggbeater kick, right?
Sure, of course.
But historically, They just relied on land-based strength tests. They would take athletes into the gym and measure how high they could perform a vertical jump or how much they could squat.
See, I always thought that if an athlete has massive explosive leg muscles, like if they can squat 400 pounds or launch themselves 3 feet into the air on dry land, that raw athletic power would just automatically translate into the pool.
A lot of people think that.
I mean, muscle is muscle, right?
You would naturally assume a strong correlation, yeah, but the research explicitly notes that dryland metrics show a very, very low correlation with actual aquatic pushing ability.
Really? Just completely different.
Completely different, and the biomechanics explain why. Think about what a dryland jump actually is. It is a split-second, explosive singular action.
Right.
You overcome your body weight once, gravity takes over, and then you land. The muscle fibers fire all at once in a massive burst.
Oh, I see. But pushing a 200-pound opponent in the water isn't a singular explosion. It is sustained. You have to apply cyclical force against a constant resisting mass.
Exactly the issue.
Because if you just explode once, you might move the defender an inch, but then you immediately sink or get pushed right back.
You immediately lose the ground you just fought for. The physical demand is a relentless, continuous drive. So a player who has an incredible one-rep max in the gym might completely lack the specific muscular endurance and, the complex rotary technique required to maintain horizontal force in the water.
Okay, so dryland tests fail because the biomechanics just don't match. But previous water-based tests had major flaws too, didn't they?
Oh, absolutely.
Because I know researchers in the past tried to measure this by having athletes wear weighted vests and treading water until they were utterly exhausted.
Yeah, the weighted vest test is a classic example of misapplied measurement.
How so?
Well, if you load an athlete with lead weights and tell them to just keep their chin above water, you are solely measuring vertical buoyancy and vertical endurance.
Oh, right. Because gravity is pulling them straight down.
Exactly. But the tactical battle in a water polo match happens horizontally. You're pushing your chest forward against an opponent's chest. A vertical test doesn't mimic horizontal combat at all.
That makes total sense. And what about the tethered tests? I read that some coaches would tie a player to the side of the pool with like an elastic bungee cord and see how far they could swim out. That seems a bit closer since it's at least horizontal.
It is closer, definitely, but it fails on the variable of resistance.
Why is that?
Because an elastic bungee cord provides proportional resistance. The further away from the wall you swim, the tighter the band gets, and the harder it pulls you backward. It acts like a spring.
Right, the tension keeps increasing.
But in a real match, a human defender doesn't suddenly double in body mass just because you push them 2 feet backward.
Wow, yeah, I didn't even think about that. A defender is a constant mass. So the bungee cord is testing your ability to fight an exponentially increasing force, which isn't ecologically valid to the sport at all.
Precisely. Which is why Croteau and his research team realized they needed an entirely novel approach. They had to engineer a way to measure continuous horizontal force against a constant mass while the athlete was fully submerged and using the Eggbeater kick.
And the solution they came up with is just brilliant in its practical simplicity.
It really is.
Because they didn't build a multi-million-dollar aquatic laboratory. They built an experimental setup right on the pool deck using equipment you could find in almost any commercial gym.
Yeah, off-the-shelf stuff mostly.
They took a standard 4-pulley weight stack machine, parked it right at the edge of the pool, and then added some incredibly precise instrumentation.
The core of the innovation there is the waterproof load cell.
Great, tell us about that.
So a load cell is essentially a highly sensitive digital force gauge that measures tension or pull. They attached this sensor directly to the cable of the weight stack, and it was sampling data at 100 hertz.
100 hertz, so 100 times a second.
Exactly. It was recording the exact microscopic force of the player's push 100 times every single second.
That is insane resolution. From that load cell, they ran a 10-meter non-elastic rope out into the water, and they attached it to a thick rubber loop that the athlete wore securely across their chest.
Yep, harness style.
By keeping the rope exactly horizontal, parallel to the water's surface at a 0-degree slope, they perfectly isolated the horizontal pushing force. No upward lifting, no downward dragging, just pure forward drive.
It's a very clean setup. And to test the validity of this setup, they brought in 33 Canadian national team players.
That's a solid sample size for this kind of study.
It is, and a highly elite cohort, too, consisting of 19 males and 14 females, ranging from the junior to the senior national levels. And, to ensure the test mimicked reality, they used a sex-specific, standardized resistance on the weight stack.
Right, I saw that. They set the stack to 54.4 kilograms for the women and 81.6 kilograms for the men.
Correct.
I was initially curious why they didn't just have everyone pull the exact same weight, or why they didn't customize the weight to each individual's body mass.
That's a common question. But standardization is vital for testing sport-specific capability. In a real match, you don't get to choose the weight of your defender.
Oh, true.
You are fighting a relatively standard opponent mass based on your competitive league. By standardizing the weight stack roughly 54 kilos for women and 81 for men, every athlete in that group is fighting the exact same constant, unyielding resistance.
It perfectly simulates engaging with an elite defender. So I'm looking at the parameters they set for the actual test, like the duel itself. Once the player was in position in the water and the rope was taut, they were instructed to push forward using their Eggbeater kick as hard as they could without backing down.
Right, maximum effort.
But they only had to do it for exactly 10 seconds. At first, I wondered why such a short window. Why not test them for a full minute to really see who has the best endurance?
It sounds short, doesn't it?
It does. But then I thought about the flow of an actual game. You rarely see two players locked in a static wrestling match for 60 unbroken seconds. Like a referee blows a whistle, a foul is called, or the ball transitions down the pool.
Your deduction aligns perfectly with the time-motion analysis cited in the literature.
Oh, really?
Yeah, researchers have actually broken down countless hours of actual water polo match footage, frame by frame, and they found that the mean contact time during these intense physical struggles between male players is exactly 9.8 seconds.
Wow. Wait, 9.8 seconds? That is incredibly specific.
It is. So a 10-second test isn't just some arbitrary laboratory number. It is the precise, ecologically valid physiological window during which a player needs to exert maximal dominance.
That makes perfect sense.
If you could hold your ground for 10 seconds, you have likely won that specific tactical exchange.
Here's where it gets really interesting, though. Having an athlete push a weight stack for 10 seconds is a great physical simulation. But the next massive challenge this research team faced was the data translation.
Oh, definitely. The data is messy.
Because you have a load cell capturing tension 100 times a second. If you just print out that raw data, it doesn't look like a smooth, readable graph.
No, not at all.
It is a chaotic, jagged line of numbers because the tension fluctuates wildly with every single micro sweep of the player's legs, not to mention the water literally splashing against the rope.
Right. Processing that raw signal requires some intense academic rigor. You really have to separate the signal from the noise.
How did they manage that?
Well, the researchers used custom Python scripts to process the data, and they applied a Savitsky-Golay algorithm to filter the raw force curve.
Okay, so for anyone who isn't a data scientist, a Savitsky-Golay algorithm acts almost like a highly sophisticated digital shock absorber.
That is a great way to put it.
Yeah, like if you drive a car over a gravel road, the shock absorbers soak up all the tiny, vibrating bumps of the rocks, but they still let you feel the major dip of a pothole.
Exactly.
The algorithm does the exact same thing to the data. It smooths out the irrelevant, high-frequency vibrations caused by the churning water or the mechanical hum of the pulley system, while perfectly preserving the true shape and the actual peaks of the muscular force being applied.
And that preservation of the true peaks is exactly why that specific algorithm is used in biomechanics. But the script was also designed to handle behavioral anomalies, which is pretty cool.
Behavioral anomalies? Like what?
For instance, it automatically ignored any quote-unquote double kicks at the very end of the trial.
Oh, I found that detail absolutely fascinating. You can totally imagine the psychology of the athlete there.
Oh, yeah.
They know they have to push for 10 seconds. When they hear the buzzer or realize the time is up, they give one last desperate, unnatural thrash of their legs before collapsing.
Precisely. It is an artifact of the testing environment, not a reflection of their actual sustainable Eggbeater technique.
Right.
So the Python script identifies that outlier spike at the very end of the timeline and surgically removes it, ensuring the final dataset only reflects the true, sustained pushing technique.
And the results of this filtration were incredible. To prove this brand new method was actually reliable, they had the athletes perform the test, and then they brought them back a week later to repeat it.
Yep, the classic test, retest reliability check.
Right. In science, you measure that consistency using intra-class correlation coefficients, or ICC values. The researchers found the test to be incredibly consistent, hitting ICC values of around 0.9 across almost all their major metrics.
And contextualizing an ICC value is really important here. In biomechanical testing, anything above a zero point 0.8 is considered highly reliable.
Okay, so 0.9 is huge.
It's a massive success. Hitting around 0.9 for variables like overall mean force, maximum peak force, and total impulse proves that if you test an athlete today and test them again next Tuesday, the test is capturing their true physiological ability.
It isn't being skewed by random daily fluctuations or equipment errors. The test is rock solid.
Exactly. It's highly dependable.
But, science is just as much about discovering what doesn't work. And the researchers were very transparent about a clear failure in the setup. Some specific metrics simply could not be measured accurately, no matter how good the Python scripts were.
Yeah, it is a phenomenal lesson in the limitations of physical equipment. The study found that any time-based variables were entirely unreliable.
What do you mean by time-based?
Well, if the researchers tried to measure time to first peak force, meaning how fast the athlete achieved their maximum push from a dead stop or the rate of force development, the reliability just plummeted. The ICC values dropped off a cliff.
So if the load cell is taking 100 measurements a second, why is the system essentially blind for the very first split second of the test? Why can't it capture that initial explosive movement?
It's a great question.
I started looking at the equipment list again, and it finally hit me. The 10-meter rope is non-elastic, but the thick loop wrapping around the athlete's chest is rubber.
You identified the exact culprit right there. The physics concept at play here is called system hysteresis.
Hystesis.
Yeah. Even with a rigid rope, the overall system has elastic components. The rubber harness around the chest and even the very slight microscopic stretch of the steel cables on the weight stack.
It is like trying to measure how fast a sports car accelerates from 0 to 60, but instead of putting sensors on the tires, you're measuring the speed of a heavy trailer being towed behind the car by a thick bungee cord.
Oh, that's a perfect visual.
Right, the driver slams on the gas, the car's engine explodes with power, and the tires spin instantly. But the trailer doesn't move yet.
No?
The bungee cord has to stretch out to its absolute maximum tension before the physical force finally reaches the trailer and starts pulling it forward. The measurement of that initial acceleration is totally warped by the deformation of the cord.
That is a flawless explanation of hysteresis. At the exact onset of the 10-second duel, when the water polo player first explodes forward in the water, the rubber harness deforms and stretches.
It absorbs the shock.
It acts as a dampener, exactly. It absorbs the initial neuromuscular shock. So the digital load cell isn't registering the true explosive force of the athlete's legs. It's only registering the stretching of the rubber loop.
And because of that elastic deformation, the researchers rightly concluded you simply cannot use this pool deck setup to measure explosive onset power. It is strictly, entirely a tool for measuring sustained force once the entire system is fully tensioned.
And acknowledging that limitation is what gives the rest of the study its credibility, honestly. Which brings us to the construct validity of the test.
Right. Did it actually measure what it claimed to measure?
Exactly. To prove this, they compared the male and female groups. Because the established physiological literature dictates we should expect to see a clear difference in absolute raw strength output.
And the data confirmed those physiological differences beautifully. The male players generated an average mean force of roughly 170 newtons throughout the 10 seconds.
Which is substantial.
To translate newtons into something more visual, that is roughly equivalent to continuously holding up 38 pounds of weight with just your legs while floating.
Wow.
Yeah, and their maximum peak force spiked to over 203 newtons.
Meanwhile, the female players produced an average mean force of roughly 122 newtons and a maximum peak force of 143 newtons. So the data showed a significant difference in the absolute force ceiling, with large effect sizes, which perfectly aligns with expected biological variances in raw power.
But the researchers didn't stop at just measuring raw power. They wanted to understand the quality of the effort. So they created a fascinating metric called the endurance index.
The endurance index is just brilliant. They calculated this by looking at the total impulse.
And impulse is force multiplied by time, right?
Exactly, over the entire 10 seconds. They compared the athlete's actual performance to a theoretical ideal. Imagine if a player hit their absolute maximum target force in second one and held that exact massive number perfectly flat without dropping a single newton for all 10 seconds.
That would be brutal.
It would. But that theoretical flat line would be a 100% endurance index.
And when you look at that specific endurance index, the gap between the male and female athletes completely vanishes.
That's incredible.
Despite the massive difference in raw force output, the endurance index was nearly identical across the board. Both the male and female groups maintained an efficiency rating of roughly 85% against their respective workloads.
And the profound takeaway here is that while the peak power ceiling changes based on absolute strength, the fundamental human capacity to sustain that relative effort over a grueling 10-second bout is a shared, universal trait among elite athletes.
That's amazing. The men might push a heavier absolute load, but their ability to endure the exhausting fatigue of that load decays at the exact same proportional rate as the women pushing their load.
Yes, precisely.
To be an elite water polo player, regardless of sex, your neuromuscular endurance essentially has to be optimized to hold about 85% of your max power when fighting for territory.
Exactly. It proves that elite endurance is a universally optimized characteristic.
So we have spent a lot of time on the biomechanics, the Python scripts, and the physics of the load cell. But for the listener who is actually coaching a team or, an athlete heading to the pool tomorrow morning, what is the practical application of this?
That's the million-dollar question.
Right. How does a piece of academic research change a Tuesday morning practice?
It entirely changes how a coach can evaluate, correct, and optimize technique. Previously, a coach standing on the pool deck could only judge an athlete visually.
Which is tough.
Very. They could see if a player was slowly being pushed backward by a defender. They couldn't see why.
Because you can't see underwater mechanics clearly when the surface is churning with all that splashing.
Exactly. But now, a coach can hook a player up to this simple weight stack system and actually look at the force curve, the specific peaks and valleys of their total impulse right on a laptop screen.
Oh, that's huge.
They can instantly see the athlete's hidden strategy. Are they relying on chaotic, exhausting bursts of force? Are they kicking wildly to generate a massive spike and then drastically dropping off a second later?
Or have they mastered the technique to apply a smooth, relentless, sustained push?
You've got it. You could effectively diagnose the efficiency of a player's invisible underwater Eggbeater kick on a digital graph.
And the beauty is that the methodology doesn't require a university grant. It uses a standard weight stack and a portable load cell. It is incredibly affordable and readily applicable to a daily training environment.
It demystifies the murky waters. It takes a historically invisible, highly practical struggle and makes it as measurable, trackable, and trainable as counting the plates on a barbell.
If you are captivated by the biomechanics of human performance, or if you want to actually see what these force curves look like, because the researchers used Bland-Altman plots in the paper to visually prove the reliability, and they're basically these fascinating scatter plots that show you how tightly the two testing sessions agreed with each other, you absolutely need to read the full article.
It's definitely worth a read.
Once again, it is titled Analysis of Pushing Forces During the Water Polo Eggbeater, authored by Croteau, Lanoé, and Clément in the March 2024 issue of the Journal of Sports Science and Medicine.
The paper is a true masterclass in solving a complex biomechanical problem with elegant, practical engineering.
And while you are looking that up, make sure you follow the channel and turn on notifications for similar content so you never miss an academic deep dive into the fascinating science of human performance.
This deep dive into continuous underwater force really highlights the difference between a visible explosive jump and an unseen relentless push. And, that leaves a final provocative thought for you to consider.
Oh, I love where this is going.
We often celebrate the explosive moments in life, the massive leap, the sudden breakthrough, the highly visible win.
We really do.
But this study proves that holding your ground against constant pressure requires a completely different mechanism. In your own life, whether you are looking at building a career, mastering a new skill, or developing a relationship, are you relying entirely on those visible, exhausting, explosive jumps to make progress?
Wow.
Or are you cultivating the unseen, continuous forces, the daily habits and relentless routines that truly allow you to hold your territory when the pressure's pushing back? Because sometimes the most powerful force you can generate is the one nobody else can see.